So lesson 29, continuous time Markov chain. So the purpose of this particular lesson is just to allow us to see how we can use a continuous time Markov chain in order to solve a problem. So I'll go ahead and write this in blue up here. So continuous time Markov chain, and we want to use it to solve a problem. For example, the problem that was in the book was example 8.3, where we're talking about this mechanic, and he forklifts came in the shop at a certain rate, and we got to sort of figure out what that rate is, and I'll show you sort of how to do that using the data that, or the information that was given, and then we use that in order to come up with the to solve this particular, or answer these particular questions using a continuous time Markov chain. Okay, so the way we start off with any of these continuous time Markov chains is define what our stochastic process is. So in this case, xt is the state of the system. So the state of the system is the number of forklifts in the repair facility at time t. Okay, so I claim that you can use a pure birth, death process in order to do this one. And why is that? Because x of t is going to go from 0 to 1 to 2, and then from 2 or 1, it can only move back and forth between the numbers there. For example, if I'm at 1, I can only go to 0 or 2. I can't. Theoretically, I guess you could, but in general, what we're talking about here is you can't move from one state to the next without going through the previous state. So in other words, it looks something like this, where you start off at state 0, and then you can only move from 0 to 1 by some rate lambda, and we'll figure out what that lambda is here in a second. And you can move to state 2 also with this. Oh, the other thing is we're going to let all of our lambdas be equal and all of our mu's be equal. So if you don't remember mu's and lambdas, you go back and check it out from our last class. And then in this case, we're going to allow, I think if you read up here, it says that 27 forklifts at the facility is the maximum. So that's what we have space for. So I will put the ... We will come in and we'll say 26. And then my last one will obviously be 27. So we have 27 plus 1, right, because I have a 0, 28 states. And we want to use continuous time Markov chain in order to model this problem. And we're making it a little easier than we did last time. So we're letting all of our mu's, all of our lambdas be the same value. Last time I think I had a lambda 0 and a lambda 1 and so on and so forth, but all of these are the same. So how would I figure out what this lambda and mu is? Well, first of all, trucks arrive at the repair facility how often? So we got to sort of read this thing and go, okay, so last year the facility repaired 54 trucks. So that probably gives us an idea. So for an annual basis, here I'll do this in green. So on an annual basis, 54 trucks need to get repaired. And then look at that. Let's just put everything in terms, instead of annual, let's put it in terms of months. So 1 month, or I'm sorry, 12 months is equal to 1 year. So 54 trucks in 1 year, and we're going to convert that to a rate in months. So lambda is equal to 54 divided by, so 4.5 trucks per month. That's what we would expect on average if we did 54 in an entire year. So this is equal to 4.5, 4.5. I put my equal sign on there, 4.5, and so on and so forth. Okay, so and then the next thing says the average repair time is about 3 days. So we have 3 days for one vehicle. So let's see, that's if it takes 3 days, then one truck, and if the person worked weekends and every day during the month, then maybe we would be happy with saying that it was 30 days in a month. But let's see, one truck is 3 days. So really the question is, what is your assumption about the number of days in a month? And I'm going to say 22. I'll say 22. I'll say there's eight weekend days. On average is about 30 days. So we'll take off 8 weekend days is equal to 1 month. So that is 22 divided by 3. Let's see, 22 divided by 3 is about, so mu. So to move from, maybe if I had 3 trucks in there and I repaired one, I would move to 2. So my mu is 7.3 trucks per month. And it's important to get these two in the same time period. It doesn't make a whole lot of sense if it wasn't. So, I mean, I could come back in here and put 4.5 in for each one of these. And we could come back in and put 7.3 in for mu. But I won't do that because it's just taking too much time to do all that. Okay. So the next thing that we want to do is we want to take this process, and like last time, we're just going to write the differential equations that correspond to the equilibrium point. So at 0, if I'm at equilibrium, then the amount going in equals the amount coming out. Or if you added them all up to equal 0. Sort of the same way of looking at this, looking at the same thing. And so in this case, lambda P0 is equal to, so that's the part that is going out, and the part that's coming in is mu P1. And I'm going to leave it in lambdas and mu's until we get down there to the end. We'll come back and use the green values here later on. But I just want to solve this thing in general before we move too much around. Okay. And so for state 1, so for P1, I have lambda. So I got mu plus lambda for P1 leaving the place, right? So I got mu plus lambda, both of those are coming out of P1. And then going into P1, I have lambda P0 plus mu P2. So again, so this involves the arrows going out. Here, let me use the cursor. This involves the arrows that are leaving the state. So if you go up here to 1, I got a mu going out times P1, and I got a lambda going out times P1. And then these are involved with the arrows that are coming into that state. So go back up here to 1, so I got a lambda P0 coming in, and I got a mu P2 coming in. So that's where I'm getting these letters and whatnot, and numbers that are coming up on here. And then we could go and find state 2, and it's going to be, believe it or not, mu plus lambda, and then P2. So there's a pattern that's sort of, and I believe we discovered this last class. And then I have a lambda coming from P1 and a mu coming from P3. And dot, dot, dot. Let's use, let's just say all of these look a lot alike until we get to number 27. So 26 will look a lot alike, and this will be mu plus lambda P26 is equal to lambda, the one before it, which will be P25, and then plus mu, the one after it, which will be P27. And then this last one's a little unique. It's just the ones coming in, I'm sorry, the ones leaving is what we're putting on this side. So mu P27 is equal to lambda P26. Okay. So now what I want to do is I want to notice something neat about these equations. Again, there's 28 equations, so it's going to be rather difficult, kind of cumbersome messing around with these. But I noticed that if I take this and I have the P1 that, so if I divided both sides by mu, I would just get lambda over mu times P0. So that would be what P1 is. And it's going to take a little bit more work, but the same idea. And I'll do the work just so we all see it at least once. So let's solve for P2. So I have P2 on one side, and then I got my mu plus lambda divided by, so I got to remember to divide by mu because we had to take care of that mu. And then P1, and then I'm going to subtract lambda divided by mu, make sure we remember to do that, times P0. Let me just look at it real quick to make sure. Okay, it looks like it's right. And then I'm going to now, okay, so we know P1 is equal to this thing. So I want to convert all of these into the same variable, into P0. So I'm just going to take that lambda over mu times P0 and substitute in for P1. So I get mu plus lambda over mu and then times P1, which is lambda over mu times P0, and then minus, we get everything else stays the same, minus mu P0, and now we're close. So now all I'm going to do is take this and multiply it all out. So I'll take, so I got a mu here times lambda over mu squared times P0. Make sure that makes sense. So mu lambda over mu squared, P0, and then plus, what is that, lambda squared over mu squared times P0, and then minus lambda over mu times P0. Okay, so we're almost there. And so this, remember what this is P2. So I'm just bringing this down and writing it again. So P2 is equal to, now I can cancel out the, so let me move my cursor. I can cancel out a mu here. So I get lambda over mu P0 minus, so now all I'm going to do, I'm going to take this one at the end and I'm going to put it in here, and it's going to be minus lambda over mu P0, and these two will cancel off. So these two will cancel off, and it will just leave us, again, all the algebra aside, it wasn't that hard, lambda over mu quantity squared times P0. Okay, so let's sort of look at the review the bidding here. I got, so this one is, so P1 is lambda over mu to the 1 power times P0. P2 is lambda over mu P squared times P0. So if we sort of put our thinking caps on, we can probably take this thing, if we had enough time, and we could show that it was equal to P3 is equal to lambda over mu to the 3rd power times P0, and dot, 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 lo and behold, if I wanted P27, so I'm going to take this guy now and put it in and find out that P27 is equal to lambda over mu. If you did all the ones before it, you'd find out that it was equal to the 27th power times P0. And all I want to do now, just real quick, I'll do it in a different color. I just want to show that this equation, this 27th one, really doesn't get used. It's basically saying the same thing that this one said. So let's see why that's true. So P27 is equal to, so all I'm doing is dividing both sides by mu, and I get lambda over mu times P26. But we know P26, if you take the one before it here, we know P26 is just equal to lambda over mu times P0 to the 26th power, lambda over mu to the 26th power times P0. So we take this and substitute it in here for P26, and we get lambda over mu to the 27th power times P0. Okay, so really we didn't use this one. So what we're going to do, just like last time, is we're going to use P1 plus P2 P2, oop, I forgot my P0, P0 plus P1 plus P2, dot, 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 all the way up to 27, because there's only 28 states if you include 0. All of that's equal to 1. So that's our extra equation that we're going to need in order to solve this thing. So we're not going to use a linear algebra to solve this one. We're going to use some algebra to solve this one, or some calculus, I should say. Algebra, I guess, is good enough. Okay, so we are sitting here now where I have, well, I tell you what, let's just start fresh here for a second. So now I have an equation for all of these different values, so that if I take, so I'm going to solve this, so solve using a general n instead of n equals 27. So I'm not going to solve it for the 27th one. I'm going to solve it basically in general. So I'm going to set Sn equal to, so if I had n equals 27, then I would have 28 states here, and I'd have P1 plus dot 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 plus P27. Oops, I'm doing it for n. I would have n of these, and we know all of those would add up to 1. So I'm going to set this Sn equal to, so now I'm going to substitute in the information that we learned just up here previously, right? So we just learned that if I want P1, then all P1 is lambda over mu times P0. And if I want P2, then I want lambda over n squared times P0. None of this mattered how far we went out with n. And if I wanted dot 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 to the nth one, it would be lambda over mu, this is a mu, to the nth power times P0. So this part did not matter when we were solving those up here. It just, the n equal 27 didn't matter. It just figures, or just depends on how far off or far out you're going to go. Okay. So now what we want to do is take that information, or take this and use it somehow. And so all I'm going to do is take this partial sum, if you will, and that's kind of what I'm calling this thing, this Sn. If you're in calculus, we did these partial sums, and we figured out what an infinite amount of these multiplied came out to be, and we ended up taking a limit. But this one, we don't need to do that. So all I'm going to do now is I'm going to take lambda over n and multiply that by Sn, and we're going to have another equation. So lambda, not n, lambda over mu. Lambda over mu times Sn. And if I do that, then it's going to be lambda over mu P0, right? So that's what's going to happen here. And then plus lambda over mu squared, right? So if I take him and multiply it by lambda over mu P0 plus dot dot dot. So all the way till we get lambda over mu, so the one before it would be to the n P0, and this one would be lambda over mu to the n plus 1 P0. Okay, so I have two equations here. All I'm going to do is I'm going to take this one and subtract, so I'm going to take the top one and subtract the bottom one. So I'm going to draw a line here indicating that I'm going to take this top one and subtract this one. So on the left-hand side of my equal sign, I just get Sn minus lambda over mu Sn, and that's equal to everything on the right. So I'm going to use a red pen here. Well, I get the P0, so P0 stays. But then, after that, this one cancels with this one. And why does it cancel? Because that's a minus sign right here. So remember, that's a minus sign. So these are all negatives. So that one cancels with that one. This one cancels with this one, and so on and so forth, all the way till we get this one goes away, and then we get to this guy. So what we're left with is just P0 minus lambda over n to the lambda over mu. It looks like an n is why I keep calling it that. Lambda over lambda over mu over to the n plus 1 times p0. Okay, so we're almost there. So now what I want to do is I want to solve for p0. I know Sn is equal to 1, so I'm going to go ahead and circle that again. If I added up all of my proportional times that I'm in these particular states, right? So all these proportions have to add up to 1. So this ends up being Sn times 1 minus lambda over mu, where this guy really is just equal to 1, and that's equal to, I'm going to take a p0 out of both of these, and I get 1 minus lambda over mu to the n plus 1. Now what I really want to do is solve for p0. So if I take those two, I set p0 equal to, again, that guy, Sn goes away, and we're just left with 1 minus lambda over mu, all divided by 1 minus lambda over mu to the n plus 1. And the only time this doesn't work is if I get a 0 in the denominator. Notice the only way I can get a 0 in the denominator is if lambda equals mu. There's other way we can solve this other ways if lambda equals mu, but for the most part, if they're not equal, then it's this very simple equation here. So I can solve for p0, and then I can use p0 in order to solve p1, because we know p1 is equal to lambda over mu times p0. So once we have p0, it's just, and we know what lambda and mu are, we just use that to find p1, and then we use it to find p2, and so on and so forth. And in this case, we're going to go all the way to p27. So it could be very cumbersome in order to do that. So we're obviously going to use R here in a second. Just want to make sure that I'm covering all of the, so let's go back to the forklift problem. So after using this equation, let's go back to the forklift problem. Let's figure out what our distribution looks like of the time that we're in these different states. So if you remember, lambda was equal to 4.5 trucks per month. And mu, our rate at which we repaired them, was equal to, let's see, around 7.3 trucks per month. That's how quickly we can get these back out. And really what we want to analyze is, so what is that distribution-wise? How often are we with no trucks in our facility, 1 truck, 2 trucks, and sort of analyze that information. So if we use this equation that we just developed, so let me go back up. So if we use this equation, we can very easily, and n, we forgot n is equal to 27 in this case. So there's 28 different states from 1 and then 1 to 27. So p0 all the way, so p0 ... all the way to p27. So this is a pretty big vector here of proportions of time. So p0, if we just use our equation that we just got, so 1 minus, so 4.5 over 7.3 divided by 1 minus 4.5 over 7.3 to the 28th, I believe. So n plus 1, so 28. We get 0. So put it in your calculator, you get 0.3835562. Oh, okay, good. So we get, I think that's the same thing they got in the book. And then what we want to find out from there is, now we got to use that to find P1. So P1 is just 4.5 divided by 7.3, so lambda over mu, times 0.3835562, which would be equal to 0.23, if you put in your calculator, 6442, and so on and so forth. Again, it would get cumbersome to do all 27 of these with a calculator by hand, because then the next one would be 4.5 over 7.3 squared times the same business. But as you can see, this is a pretty simple thing for the computer to do, right? So I can make a little script that will do this for us, and we can graph it out. We'll make it look pretty like the book does. All right, so if that's what we want to do, let's go ahead and stop sharing OneNote and then jump over to R. All right, so we have RStudio up, and then what we want to do is put in this problem. So this problem starts off, if you put in the parameters, in other words, lambda is equal to 4.5, mu is equal to 7.3. I'm going to call it rho. That's what it's called in general. The lambda over mu is generally called rho. Lambda divided by mu is just going to help us put in this formula in very easily. And then I'm going to go ahead and solve for P0. P0 is equal to 1 minus rho, lambda over mu, divided by 1 minus rho to the, I think this is 28th. Sure that we get what we expect. So if you look over here, you'll see 0.38. Okay, so that is the same thing that we got earlier. Okay, so that's good. And then, I don't know, let's go power. All my powers are going to be a sequence from 1 to 28. 1 to 28. Yes, that looks good. I'm going to set P equal to 0. And then let's see, let's do a for loop. For I in 1 through length of power. What do we want? P. We want P sub I. So P1, I want that to be equal to whatever my initial P0 is, and I want to multiply that by, you can either do rho, that's what we'll do. We'll just do rho to, not rho with a W, rho to the power I. Let's see what let's print P. Sure, that's what we expect. Yeah, so 0.236. I think that was that was the next one, P1. So we don't have P0 in there, so we'll add that one whenever we pull up the data from. Matter of fact, let's just create it now. So let's call it our results, or our result is equal to data dot frame. And then I want xt to equal 0 to 27. So that's the state that we're in. I want P to equal, I'm going to put in P0 in the front and then P after that. So that's the P that we just created. And I'm not very fond of all the to the negative, all that business. So I want to do, I'm not very fond of the exponential, the scientific notation down there. So I'm going to go ahead and tell it to round to maybe 5. And then let's print that off, see what happens. Oops, looks like I messed up somewhere. Let's see here in data frame. Arguments imply differing rows. So 0 to 27. Oh, I know what it is. So I should have went to 28 here. I should have just went to 27. Let's calculate this thing again. P and then result, and then print result. All right, so if I print result, we get 0.38. So let me turn to the book to make sure these are the same sort of numbers that they get in the book, because that's important. So 38%, 24%, 15%, and so on and so forth. Okay, so now what I want to do, I mean, we could look at this little vector all day and say, yeah, we achieved success. But I'm going to show you how to throw it in a chart. So we'll let BB equal bar plot. So let's start with P0. And let's go, it looks in the book, like the book they only went to 10. So I don't know, let's just go to 10 as well. So I'm only going to put in the first, and that's not a small p, it's a capital P. So we're going to put in 1 through 10 of that, and that'll be where our bars are. Let's see, if I wanted to label it, you got to do names. And I had to look this up in Google, by the way. I didn't remember how to. So if you just put label in a bar plot, then it'll come up and tell you what to do. And then so I'm gonna check. So that's equal to 0, and then it's gonna go all the way to 10, I believe. Let's find out what happened. So it looks like that's what's happening here. Okay, so everything looks good. The problem is I want this to go up a little bit higher. So I'm going to say ylim is equal to, let's see, my smallest, and then my highest is maybe 0.4. So that's where we'll put it. And then what I want to do is I'm going to throw the text in. So I want it to look sort of like the books. And if you do this, it'll put the picture or the percent, not necessarily the percent. I'm not going to worry about the percent. We could probably do that, but I'm just going to put the number right above it. So I'm going to let it be. So the text that I'm going to put up there is P0 and P. So it'll go in and it'll put for each one of those bars, it's going to put a number corresponding to what these texts are, right? So it's going to put in the P0, and then it'll start at P1 and 2 and go all the way to 10. Actually, I probably need to do 1 to 10. I probably need to tell it only to stop there. Otherwise, it'll probably think it's going to do them all. And then what I'm going to do from there is I'm going to add 0.02. So in other words, I want it to be a little bit above the bar. You could go below the bar, but the problem is if you go below the bar, you're going to get in issues down here when you just don't, your bars just aren't that big. Sometimes people do that one. And I'm going to label, so my labels, yeah. So just so you know, this guy right here is telling you where to put it. So for example, it's going to go to the top, and then it's going to go 0.02 above it. But the question is, well, what do you put there? And then that's going to be this round. So I'm going to round because I don't want to see a whole bunch of numbers down there. And I'm going to round the entire P0 to P. Again, we're going to go from 1 to 10. And then I want to round all of those to maybe 3 digits. All right, and then that should work. Control Enter. And then it's kind of big, so maybe we make it so that the text is smaller. Maybe CX is equal to 0.8. We got to run both of them again. Control Enter. Maybe we go up a little bit further than 0.4, maybe 0.43. Let's see what that does. Good. So that does about what we want it to do. So it puts in the percentages, and let's just make sure that it aligns with what the book says. So the book has this one, and it's going up to 38%, it says, then 24% on this one, 15%. It looks like it's all lined up. Okay. And then it goes out and it says 10, and it doesn't have any of the percentages down there, but at least I have the decimal place down there to go with that. All right, that's all I got for this class. I will see you guys tomorrow, where we will do another problem that's similar to this one. So I'm expecting everyone to hopefully have seen this video and can follow along, because I'm going to go fairly quickly. All right, thanks.